Hi, and welcome to the New York City Category Theory Seminar. This is the last seminar of the fall 2021 semester, and we have the honor of having Todd Trimble. He's going to talk about categorifying negatives, roadblocks, and detours. Last time he spoke about bar construction. That was a beautiful talk. Take it away. Todd, we have this thing that you have to tell us something about, where you did your degree and where you come from beforehand. Take it away.
So I was born and raised in Richmond, Virginia. That makes me a son of the South. And I did my undergraduate degree at Johns Hopkins and my PhD at Rutgers, getting a PhD in 1994 under Miles Tierney, who is sadly no longer with us. My thesis topic was in so-called categorical coherence theory, and mathematics took me around the world to Australia, where I met a lot of wonderful people, but I'm glad to be back in the States. Teaching since 2019 at Western Connecticut State University. And it was a pleasure meeting you, Nosen, again, after many years. Almost 2 years ago is when I gave a talk on the bar construction.
Right.
So there you have it. Good evening, everybody. I'm very pleased to be invited to give this talk. And so shall we begin?
Please.
Oh, hang on. Here we go. Okay. So I have a little brief outline here, which you're welcome to peruse. In case some people here don't know what the word categorification means, I will explain what that is, starting off very gently with a few examples. And on request from Nosen, he was curious or sort of nudged me to say a few words about what Shanuel might have had to say about the idea of a negative set, which is really the theme of tonight. So I will be touching upon some of his work there. And then I'll be looking at multiplicative negatives a little bit and what it means to categorify those. In other words, how to be categorified reciprocals. And then I'm going to meander back to negatives and discuss, some of the issues that there are in trying to find a categorical or structural analog of negating the negation operation or the minus operation. And I'll hook back into really the roots of the subject of subtraction, where back in the Renaissance, one had the advent of double entry accounting. And I think all that was maybe formative in getting the idea across of what subtraction means on a very practical level, at least for the merchants and accountants in Renaissance Europe. And so I will be looking at that in a structural kind of way. I'll tie back in with Shanuel by speaking about Euler's formula, and then lastly, I'll talk about the rule of signs. I will say right now, I'm using this talk as a bit of an excuse to talk a bit about a recent paper that I was involved in with John Baez and Joe Moeller, which is called Sure Functors and Categorified Plethism. So when we get to that point, I'll describe a little bit about that. But let's start off with categorification. This is my own attempt at a definition. You can read that for yourself, but I want to lay a special emphasis on the word art, because categorification is not really a mechanical process. It's something of an art form in which you try to lift up ordinary facts about ordinary mathematics involving equations between things and lifting them up and seeing them as shadows of isomorphisms between structures. So that's the kind of the basic idea. You kind of lift up into a higher categorical dimension, and then often sheds a lot of light on what's going on down below. So that's a rough definition. I expect that many of you, if not all of you, have seen instances of this idea, but I will go through quickly a few basic examples which should be familiar on some level. So down below, when we are in grade school or maybe middle school, we will learn about the exponential laws that hold for numbers, which looks like that. When I began learning about category theory, I was very impressed by the fact that you could see this basic exponential equation as I say, a shadow of more structural facts. When I first learned about this, I felt like I was privy to a secret. So the idea is that these numbers, at least natural numbers or cardinals, can be thought of as isomorphism classes of sets. And then this equation, this exponential equation, can be understood as follows. The exponential itself can be regarded as the cardinality of a Hom set. And then one has a natural bijection, which is very famous, where the number of functions, or rather the set of functions from A cross B into C, is a natural bijection with functions from A to the function set going from B to C. And then when you so-called decategorify that, when you pass to isomorphism classes, you get the exponential equation above. I thought this was wonderful, and the fact that you could understand other laws of arithmetic in a very similar way, I thought was just a fantastic thing. So that was sort of a beginning of it for me. Another place where this so-called categorification arises is in what people call bijective proofs in combinatorics. So if you've ever studied combinatorics or combinatorial identities, as in the book by Knuth, Graham, and what's his name, Otashnik or something like that, but Potashnik, they proved this Vandermon's identity, which I have stated this as an algebraic identity. So let's regard this binomial coefficient R choose J as being something like a polynomial in R, and similarly for S choose K. And then you got this very nice, neat little identity here, which, if you wanted, you could prove this by slogging out the algebra, just writing out the polynomials and watching what happens. But it's a lot more fun to try to understand this from the standpoint of statements about sets and bijections between sets. So if you've not seen this before, I'll go through how you might establish this. Let's look at the left-hand side. The left-hand side is a binomial coefficient. For now, I'm going to think of R and S as being cardinalities, finite cardinalities. And so the left-hand side is counting the number of in-element subsets of a set with R plus S elements. And so looking at the left-hand side, suppose you are given an in-element set, which I'm going to call capital N, of R plus S. Now we're going to count this, and we're going to consider this in a new way. Looking at the right-hand side for guidance, let's intersect this subset in with R and S separately to form two new subsets, J and K. And this will establish a bijection whose inverse, if you want to retrieve capital N back, you just sum together those two subsets, J and K, and they'll reproduce in. So you get a natural kind of bijection between in-element subsets of R plus S. I'm going to use my cursor here. Why am I just speaking? So an in-element subset of R plus S is in bijection with a pair of subsets, J of R and K of S, where if I set little j to be the cardinality of big J and same for K, then those two numbers must add up to the cardinality of N. And when you consider all the possibilities here, you wind up with this right-hand side, and voila, you've proven this for all R, S, and N. And the polynomial identity, if that's true for all integers, the polynomial identity would automatically follow. So that's a very nice kind of bijective proof of the type that combinatorialists are in love with, and there are many more examples of this. Some get very fancy. So that's another example of categorification. I need to kind of trying to keep track of where I am here. Okay, I see the time. Okay. Here's another example. So, I mean, we all learn in grade school this idea of cancellation, that if you have A plus C equals B plus C, then in essence, you can cancel the C's and derive A equals B. Now, I want to see this as descended from a more structural sort of statement. So looking at the left-hand side, I'll regard this equality here as something that you can evidence by giving a bijection between sets of these appropriate cardinalities. So let me pass over to here. We're going to lift these cardinals up to what I'm going to call a categorification. Getting back to the idea that categorification is an art, it's not always clear at the outset how you categorify, but I'm going to categorify by thinking of A, B, and C as cardinalities of finite sets, let's say. And then think of this as indicating an isomorphism between the objects of this permutation category P. So let's imagine that we have evidenced the equation here between these two sets by means of a permutation between them. So I'll say here's A and C. Here's another copy of C on the other side. So we're considering an element of this Hom set, this Hom groupoid. And what we want to do is we want to conclude that A equals B. In other words, what we would like to do is we would like to produce from this permutation, we would like to produce a permutation from A to B and do so in a natural kind of way. So without making bizarre or arbitrary choices. So this is beautiful. I mean, if you haven't seen this before, this is a very nice trick that I learned from Joyces. We're going to perform an operation which is called tracing. So you start off with this permutation from A plus C to B plus C. And then what I'm going to do is say this. We're going to produce a bijection from A to B as follows. Let's take an input A, and if the original permutation takes it to an element of C, then take that output and feed it back as input until you get back here, and keep going until you wind up at B right here. So in this tracing operation, you kind of wind around and you wind up here. You might have to do this several times. So if you start from this element here, you wind around, feed this output back into an input, apply the permutation again, output back to an input, and then bang, you land in B. If you cycle around enough times, then you're going to land in B, is the point, as long as C is a finite cardinal. So this is really, I think, quite striking proof of this very basic fact that we learn in arithmetic. So I say, I don't know who's originally due to, but I learned it from Joyces. So yes, we have this tracing operation.
What happens if an element goes from C to the same element in C?
That's fine. You ignore it. So we're only interested in the permutation from A to B.
Well, then you'll never. I mean, if it goes, yeah, it goes from itself. You'll never reach that element starting.
Right, okay. Sorry. Good. Sorry.
So we have this tracing operation, which is let's say a natural operation, at least in A and B. And it's a so-called extranatural or dinatural transformation in the argument C. So it's very natural, no axiom of choice or arbitrary choices. Using this idea of tracing in a monoidal category, so that you can generalize to a monoidal category, there's a nice paper by Joël Street and Dominic Verity, in which if you have a monoidal category with a trace structure similar to what I've given, then you can produce a compact closed category in which one formally adjoins dual objects, which play a role similar to negatives, let's say. You can adjoin dual objects and formally adjoin units and co-units, which at a string diagram level would correspond to caps and cups, and be able to produce a compact closed category. And what one gets here, if one closes up under duals, so to speak, when applied to the permutation category, yeah, you at the string diagram level, you would join caps and cups, and eventually you wind up with a new category, which is compact closed. I'm going to call that P prime, and it turns out to be something which is reasonably compelling from the standpoint of low-dimensional topology. Namely, those little strings that can loop around give you oriented one manifolds between oriented zero manifolds, which are the same things as signed sets. And with that in mind, if you look at the connected components of this compact closed category, then you wind up with the set Z. So in a sense, you can think of this as giving a kind of categorification in which you reproduce something you get by adjoining negatives, and you can get negative numbers as dual objects in this kind of way. In some ways, this is not completely satisfactory, but we'll contemplate other possibilities in just a minute. The last, somewhat more advanced example is a very interesting paper due to John Conway and Peter Doyle, I think his name is, in which they show that they prove without recourse to the axiom of choice that if you have evidence, if you have a bijection between a coproduct of 3 copies of A and 3 copies of B, then you can set up a bijection in very explicit form between the sets with cardinalities A and B. Okay, so I'm going to go through this very quickly. The paper is very clever and subtle, and there's really no time to discuss this, but I'm just going to point out a few little things. This came up on Math Overflow. It was really David Roberts who asked, is the proof of Conway and Doyle constructive in a sense satisfactory to constructive mathematicians? So they say they don't use the axiom of choice, but does it really meet the highest standards of constructive mathematicians? Andre Bauer, who always has interesting things to say, said, nah, not quite. There are little fiddly things that you need to decide that violate constructivity. So we answer the question, but somehow I feel that there is something that was left somewhat unsaid in the Conway and Doyle paper. True, what their production of this isomorphism may not be a constructive one, but what was left unsaid, I think, is that, or at least I'm pretty sure that what they have done is they've constructed a map which is actually natural in A and B. So Conway and Doyle never quite say that. They kind of hint at it, but I think that's really what's going on, and that makes it fit firmly under the ambit of categorification in the sense that I'm speaking of now. So I think that's quite nice. Okay, so those were a few simple examples.
They also finish off the paper by saying that they're hoping that I forgot the guy from Princeton, that he proves that arithmetic is not consistent.
Edward Nelson. Yeah, they say somewhere it's not that we don't believe in the axiom of choice, something like any more than we believe in the existence of infinite sets themselves, or something along those lines.
Right.
And they kind of allude to Edward Nelson, who actually thought that piano arithmetic
Was inconsistent.
So that didn't quite pan out. That was the basis of an interesting conversation over at the In Category Cafe that Terry Tao got involved in. So that was, you can look that up. I'm going to pass on to Shannon. I'm sorry, go ahead. No,
sorry, just a quick question. Is there anything particular about the number 3 here?
3 is the first hard case. So you can,
so
actually 2 is an interesting case. And it's not trivial. So if you want to have a go on your own at doing the case for 2, I would encourage it. It's not trivial, but it's a heck of a lot easier than the case for 3. And they remark that once you get 3, then you can do anything. You know.
I think there's a nice YouTube of Conway giving a talk on this, in which he does too, and he shows why you can do it.
Good. I don't know that one.
I remember seeing it, and
I'll check that out.
So
yeah,
then you can do
Conway
any
is
number.
at that paper. No, well, Peter was the one who wrote that paper that I'm alluding to. And he says, well, Conway's never quite approved of this paper. He says it's full of fluff, so I take full responsibility. Peter should have said natural. You know, he should have. Some people don't like the word natural, but he should have said it.
So then you can find the similar natural map for any n, or maybe including even the countable, the natural numbers, the countable.
Yeah, natural
case.
numbers will not float. You know, if A and B are finite, that's not going to float. But
Right.
Oh, but for any finite natural number, yeah.
Interesting.
Yeah, they say once you crack 3, you can do anything. It's an interesting result. I'm going to pass on to Shanuel and what his take on negative sets. So he has this very interesting paper, negative sets have Euler characteristic, which will play an important role for us, and dimension, which will not. But the way that Shanuel sets out the problem is he has literally this square, which is not quite a commutative square, but the intent is that we know that that the natural numbers can be categorified into finite sets so that coproducts in finite sets correspond to sums, and products, Cartesian products of finite sets correspond to products. And the question is there a way of enlarging the category of finite sets with coproduct and product to a larger category E, so that when you take the isomorphism classes of those objects, then you wind up with the arithmetic structure of Z, the integers. So notation I'll be using throughout this talk is this I of C. It will denote the set of isomorphism classes of the category C. And so if you passed isomorphism classes, then we'll have this identification. Can we similarly categorify Z? And the answer is definitely not. You can't do this as stated. I want to call that a roadblock. Just this big block in the road that seemingly can't be undone or gotten rid of. So let me indicate why that's the case. So you ask the question, well, why not? So in a category with coproducts, the statement is that if you have a coproduct of 2 sets, which is the initial object, then the individual sets are forced themselves to be initial. So you cannot have any non-trivial situation where the coproduct adds up to 0. Why? Well, we're going to think categorically. If for every object X, this is in a general category with coproducts, if A plus B is initial, so that would mean there's exactly one map from this coproduct to X, then that would mean, according to the universal property of coproducts, that there's exactly one pair of maps, one from A to X and one from B to X. So exactly one map here, one map here for any X, and that immediately implies that A and B are initial themselves. QED. Well, okay, what to do about that? So seemingly the answer is just a flat no, but Shanuel says, well, let's think about this a little bit further. Maybe we can say something about this. So here's his little detour getting around that roadblock. Can we at least find a distributive category? So that means a category with coproducts and with products, and the products distribute over the coproducts. Can we find such a category E so that its isomorphism classes has Z as its cancellative reflection? So the cancellative reflection of a rig, let me pause to say that we are dealing with rigs now. The isomorphism classes of these things have an addition, they have a multiplication. but the addition does not form an abelian group. You don't have negatives. So you remove the in from the word ring and you get the word rig. So it's like a ring without negatives. Okay, so there's such a thing as called the cancellative reflection of a rig. So if you start off with a rig here, then you mod out by the equivalence relation where two elements are deemed to be equivalent if you can find an element C where they add up in such a way. Okay, so is this possible? Already, this requires a bit of creative thinking. So this is the art of categorification, coming up with examples of such things. Chanuel had a very interesting example of where this arises in practice, where he is able to apply his ideas on Euler characteristic. I will attempt to describe one of the possibilities involved here. So what we're going to imagine here is taking E to be a category of so-called semilinear sets. So you imagine things like polyhedra, intervals, disjoint unions of polyhedra, any Boolean combination of polyhedra in Rn, basically. So any set in Rn, I'll assume the sets are of bounded extent, that can be defined in terms of this basic structure where you allow yourself to talk about addition and scalar multiplication and allow yourself to talk about the less than relation. So if you can first order define a set in this language, then you call it semilinear. Those are the objects, and a morphism from one semilinear set to another shall be a function from one to the other, so that when you take its graph, you get another so-called semilinear set. Let me just pause for a minute and say a little something about these functions. So when we teach our calculus students, when we try to illustrate the idea that some functions are discontinuous, we might draw a picture where you have what do you call them, a piecewise linear function, but where the little line segments don't hook together, they're sort of disconnected. So you can illustrate very easily the idea of limits and continuity by illustrating piecewise linear functions which are not continuous. So I want to make that point very clear that these functions here, they're not topological in nature, but they're a little bit more fine-grained. You've got more than just a continuous piecewise linear functions. With that in mind, there's a very cute little calculation here. So I'm going to imagine that we take the with the, oops. Can you still hear me? I want to check. You can hear me? I'll ask Raymond. Can you hear me?
No, I still hear you. It just said the recording went off. I'm going to have to combine the two things. But the recording is now okay. It's fine. Go on.
Okay, great. So then you could take two copies of that open interval and slide them right next to each other, but leaving a gap of 1 point between them. And let's insert that 1 point. So you take 0, 1 and 1, 2, and you stick in 1 and you get this isomorphism in the semilinear category here. Interesting. So, all right, when we pass to isomorphism classes, we have an equation. And if we pass to the cancellative reflection, then that would mean that we could cancel off a copy of I0 from the right and left side and come up with something where it come up with an equivalence that suggests that we think of the open interval as playing the role of -1. So, I mean, I skipped over something here. Chanuel proves in the course of things that we have, he actually identifies what is the rig of isomorphism classes in question and spends a fair amount of time actually establishing this result. But the idea is that X, when you map it over here, X is interpreted as the open unit interval, and X is equivalent to 2 times X plus 1. So interesting, the open interval should be thought of as being -1. So in that kind of refined sense, in the sense of this detour, we have produced negative sets, And similarly, if you take any set A, if you take any semilinear set A and Cartesian product with the open interval, by distributivity, you would wind up with 0 again in this equation. So negative sets. Okay, now Shanuel has bigger fish to fry. He has a series of papers which explores the idea of the Euler characteristic as an extremely fundamental concept which revolutionizes our very idea of what a number is. So I will point out that there's another paper of his I will recommend to you, a paper called "What is the Length of a Potato?" And there it's subtitled "Introduction to Geometric Measure Theory," but there too the Euler characteristic is the star of the show. So we'll be getting to that later, what the Euler characteristic is, but it is a finitely additive measure from objects to the integers, which is the only sensible numerical invariant. But he will define the Euler characteristic of a commutative rig as being the quotient. It kind of slipped off the edge of the slide, but it's the canonical quotient map to the cancellative reflection. That's just how he defines it. We're going to come back to Shanuel and so forth, but I'm going to move on to a slightly different topic. So we might consider the multiplicative analog of all these things. So, right, you might ask, is it possible to form reciprocals? But I mean, that's subject to the obvious objection, which is a dual form of our first roadblock. And so that would say that in a Cartesian monodal category, the product of two sets is isomorphic to the terminal object, then those two sets or two objects are both terminal. All right, what to do? Now here, there are other possibilities that are open to us, which have been massively explored. So we're going to, again, take a little detour here and think that, okay, that's not necessarily a hard no, but maybe we can expand the context a little bit so that instead of thinking about, let's say, topological spaces and continuous maps, we can instead work up to homotopy. So the idea is that instead of working with literally a one-element space, maybe you could expand your vision and think of that as being a representative of any contractible space. So one, we can replace one if we like by maybe a contractible object or a weakly contractible object, and maybe hope that you could form reciprocals with this expanded meaning. Okay, a lot of people do things like this. So let's have a little think about it. So to maybe put a finer point on it, I will describe an extended detour. You have to go down this path a little bit further. It turns out to be not exactly reasonable to hope to produce a contractible space so that given an object, you can Cartesian product with a reciprocal. It will be hard to find a reciprocal in which you get homotopy equivalence on the nose like this. But instead, what you can maybe do is hope that given one of the objects, let's say B, produce not a Cartesian product homotopy equivalence, but more of a fibration. So you hope to be able to find a space E over B whose typical fiber is the other space A. So it would be saying in a sense that, let's say E, which we think of as being 1, divided by A gives you B, something like that. So we will interpret this actually in a slightly different sense, which I'm going to call local. And the idea should be that you've succeeded in so-called reciprocating if, well, you don't necessarily have this, but maybe you can pull back the situation along, for example, an open covering of B, so that when you examine the situation in this new slice, then you actually do form a kind of reciprocation here. Just to make sure that's not a completely trivial statement, demand that the pullback functor reflects isomorphisms, or in other words, preserves all the distinctions that you originally had. So that's a rough way of putting it. So this may be possible. And I mean, this comes up all the time when you speak of things like de-looping a space, as people will. So last time I gave a talk in the New York City category theory seminar, I spoke at length about a bar construction, which in effect does this. So if you're given a topological group G, we form in a way that turns out to be very fruitful. We form a reciprocal of a topological group G. And the way we do it is to cook up a space, a contractible space, or in fact a contractible group, which I'll call EG, in which the original group embeds by group embedding. And then when you pass to the quotient by the action of G on EG, you get a so-called classifying bundle for principal G bundles, but think of BG as being an instance of this reciprocation. By the way, I had a note 0 and a note 1. When I released the slides to NoSun, there are sort of after notes. So there will be a slide that says thank you, and then there are a bunch of slides after that which amplify on some of the points that are being brought up here. I'm not going to go into the notes in this talk, but you're certainly welcome to peruse them whenever you feel like it. Okay, so there's some notes there. Now, I'm just going to make a few brief remarks about this. In the usual way of doing things, one shows that this vibration here is locally trivial, meaning that there's an open cover of the space so that when you pull back to each of the open sets of the open cover, you get a so-called trivial G bundle. That's sort of, let's go back a minute. That's sort of instantiating here. A trivial G bundle will be where you get G cross U projecting down onto U. Okay. Now, I didn't want to talk about all that. I'm admittedly being a little bit slick in this discussion here. The main point is that if you want to produce this sort of local triviality, then you can actually pull back along P. So you can take an object and a slice over EG and then pull back along itself to get this new thing, which is a trivial principal G bundle. And it turns out that this P star reflects isos. Yeah, I don't want to say too much about this. I'm just going to remark quite briefly that in the business, this turns out this fact here that when you pull back, you get an isomorphism. This fact expresses the idea that this principal G bundle is a G torser, if you happen to know what that is. So that's encapsulated in this statement here. It's a G torser in the slice category where P is an object over E over G. Okay, that's all I'll say about that. It's just that reciprocals come up frequently and very fruitfully, and it's a very worthwhile thing to consider. Reciprocals are a good situation. They're a kind of success story. But now coming back to negatives, I'm going to ask a question. Is it possible to mimic these little sneaky little detours that we use in the case of reciprocation? Can we mimic those techniques in order to get back at the problem of constructing categorified negatives? That's the question. Well, I'll say not exactly. That's a second roadblock. So here's the trouble, is that if you're working in a so-called extensive category, like a category of topological spaces, you don't have a lot of leeway in as you did in the case of a terminal space. So for the terminal space, you can fatten it up and to a homotopically equivalent thing, but much larger with a lot more room But there's no space that is homotopy equivalent to the empty space, except the empty space itself. You can't sort of expand out, and you can't fatten up to do sneaky little tricks. So that is another roadblock in our way, is that this idea won't quite pan out like it did for reciprocals. So instead, what we're going to do is we're going to go back and sort of rethink along lines similar to what Chanuel was doing, and take very seriously the idea that Euler characteristic is in fact our friend. Chanuel is a huge fan of Euler, says that Euler really revolutionized our concept of what it means to count. And so Euler characteristics play a large looming role in Chanuel's work where he explains these things. And it's important for us too. So I'm getting to the point where I'm going to begin discussing this recent paper that I mentioned, written by John Baez, his former PhD student Joe Moeller, and myself, called Sure Functors and Categorified Plethism, which you can find on the archive. There are various notions of TwoRig. Chanuel, some slides back, talked about a distributive category where you have coproducts and products, and distributivity. We're going to define TwoRigs to suit our own purposes, where we wish to discuss aspects of representation theory called sure functors. You don't need to know what those are. But for us, a TwoRig means actually not an ordinary category, but a linear category, meaning the category enriched in a base category of vector spaces over some ground field. Technical aside is that we want the ground field to be characteristic 0. That's a technical point. But the basic idea is that we define a TwoRig to be a linear category which has finite coproducts and which has idempotent splittings, kind of the most basic kinds of colimits that you would like to have, together with a symmetric monodal structure. What is going on here? Symmetric monodal structure that distributes over those coproducts. So it has a very categorified rig-like flavor here. And the idea is that these TwoRigs come up quite a lot in algebraic topology or in representation theory. Simple example would be where the TwoRig, the objects will be vector bundles over a given space, and those, you can take coproducts of those, and the symmetric monodal product will be the usual tensor product on vector bundles. And it's a very basic kind of example. But the idea of the paper was to explore the inner deep structure of the isomorphism classes of these TwoRigs. And in particular, passing to the Grothendieck group or ring, where, yes, you start off with the rig of isomorphism classes of this thing. So it's a rig, but then you throw in negatives by tensoring with the integers, tensoring over the natural numbers. And what turns out to happen is that you get a very rich structure called a lambda ring. We explained what that means in the paper. Again, you don't have to know what that is. But we start off, well, our point of view is that we start off with a simple concept of TwoRig, and then we milk out of this all the very complicated structure of a lambda ring from that, based on various decategorification techniques. But in particular, we need to really have a thorough accounting of what it means to adjoin negatives to this, and how we can think about this in a categorified way. So we're going to come back to this, and we're going to start at the beginning, and we're going to imagine, how do we teach our undergraduate algebra students, meaning students in an abstract algebra course, how do we teach them how to construct the ring of integers? Well, we might say something like this. You take the natural numbers, and then in essence, you define integers as suitable equivalence classes of pairs of natural numbers. The idea being that, you think of a pair of natural numbers as representing their difference. So that's the kind of idea of the construction. And we're going to mimic that construction. So we're going to form this ringification of a rig R. This is its ringification. We'll perform it in 2 steps. So the first step is to get suitable ordered pairs. So what we're going to do is we're going to form the polynomial rig over the natural numbers, and then let's mod out by saying, deeming that x squared is equivalent to 1. And well, that's not the integers, but we'll take that and tensor it with R, and let's see what we get. So we'll tensor this with R. We'll get R adjoin X over this congruence relation. And we can represent elements in this quotient rig as expressions of the form C plus dx, where C and D belong to the rig. Okay. Now, the whole idea here is that this is ancient. It certainly goes back to the Renaissance, as I was alluding earlier. We can think of a 2-column ledger in accounting, where we have a credit column and a debit column. And we'll think of the debits as being sort of in a negative column and this in a positive column. So credits and debits, those are the elements of this quotient rig. And continuing that thought a little bit, we can describe how to multiply 2 such elements just by simple expansion. So you just expand down, and then remember the fact that x squared should be 1. And so if you rewrite this in terms of ordered pairs, then you'll get CC, if you multiply these 2 pairs, we get CC prime plus DD prime here in the credit column, and CD prime plus C prime D in the debit column. And that's how you multiply. Okay, now this is something that's not hard to categorify. So if R is a 2-rig in the sense that I spoke of earlier, then you can form a new 2-rig consisting of pairs of objects belonging to the old one, and these are multiplied according to the same rule. So I'm describing the tensor product on this 2-rig consisting of credits and debits, so to speak, and it follows the same pattern as up here, which I'm going to rewrite to make it look a little bit more suggestive to us. So I'm going to just write down the same law, but in slightly different notation here. And you might recognize this expression if you have a little bit of experience with algebraic topology and graded objects. What in essence I am doing is I am considering the object of this 2-rig as being a Z mod 2 graded object. Meaning, so you have grades even and odd, and I'm describing the rule for tensoring 2 such graded objects. This is the usual rule that one would learn in algebraic topology. So I am thinking of this new manufactured 2-rig as a 2-rig of Z mod 2 graded objects, and I'll G for graded here. I'll use this notation throughout. Okay, that's step 1. So we form pairs. And then step 2, what one does is form a set of formal differences. These are cancellation equivalence classes in the same sense that we spoke of before. I'm reminding you what a cancellative rig is. But formally, when we actually think about how we're going to multiply these formal differences, we actually wind up with the exact same rule as we did above here. So, I mean, this really mirrors the fact that our first step was the correct step. This is the correct way to multiply these formal differences. Now, these formal differences won't categorify directly, but nevertheless, in things like K-theory, we talk about virtual differences between pairs of isomorphism classes. And so the idea is that we form the K-theory of a 2-rig, yes, by throwing in negatives to the rig of isomorphism classes, we get a ring, and we get a quotient map, which takes a pair of objects of the 2-rig and sends them to their virtual difference like that. That's a quotient map, which I'll call Q. See, how are we doing on time? We're doing great on time. I might be speaking too quickly. I don't know.
In that case, let me slow you down quickly
Yeah, go
and
ahead.
ask that this is looking a lot like, I guess, what's called the Grothendieck group construction. Is
It
this
absolutely
the
is.
same? Huh?
Yes, it absolutely is.
Okay. So is this a generalization of that, or the same thing in a different setting, or?
Yeah. So we are in. Yeah. So when one speaks about K theory, one typically applies this two move operation where you pass the isomorphism classes and then ringify. That ringification is the Grothendieck group construction, as you were saying. So there's no difference at all. That's just that's another piece of terminology that goes with this. So I am, but the problem now is to try to understand what structures along the lines of lambda rings, if you happen to know about that. How do you account for negatives in the study of lambda rings is one aspect of what our 3-author paper was about. So it turns out to be not hard to understand at the level of TwoRigs what the plethism structure is at the level of rigs, but when you begin throwing in negatives, then subtle difficulties arise, which is what I'm getting at right now. So I'll explain it in just a moment. Is there a follow-up question about that, or anybody want to interject something else? Okay, so we have this quotient map. Okay, now comes a beautiful idea. I'm not sure exactly where it came from, but I think I might have learned this from Joel. So there's the so-called Euler formula, which is absolutely critical and important in this study. So let's imagine that we're taking a Z mod 2 graded object, where those individual components are coming from the 2-rig R. And suppose, moreover, that we don't have just this structure, but suppose we equip it with some more structure in the form of what I'm going to call differential structure. So what I'm going to do is form a chain complex. Or imagine that it's equipped with a chain complex structure given by boundary maps which mediate between these two components. So a boundary from C0 to C1, from C1 to C0, satisfying the usual equations that you need for a chain complex, that when you compose two adjacent boundary operators, you get the zero maps. And I'll assume that exact sequences will split. We can speak about exact sequences in our 2-rig. I'll assume that they split uniformly. And then there's this theorem, which in some sense is due to Euler, which says that the Euler characteristic of the graded object without the differentials equals the Euler characteristic of the thing that you get by taking homology of the chain complex. So back in Euler's day, I mean, obviously he did not have any notions of homology or anything like that, but the analog would come up in something like graph theory, where if you have like a graph with some vertices constituting a set C0 and some edges forming a set C1, you take the difference between the numbers here, you should get the same thing as the number of connected components of the graph minus the number of a minimal set of generating cycles, might be a way of putting that. But after a long time, Euler was working with the famous formula V minus E plus F equals 2, where the Euler characteristic first made its appearance, but it certainly has sort of simple one-dimensional versions too, which undoubtedly he knew about. Okay, well, this is a theorem about homology. And I have a note where I go into how you would actually prove this. So the Euler characteristics are the same, and this turns out to be a very potent tool. So let's imagine then, taking this seriously, instead of thinking just about Z mod 2 graded Z mod 2 graded objects, we'll imagine contemplating Z mod 2 graded chain complexes, so having this differential structure. Now we have two rig maps. So those are TwoRig maps preserve, all the designated colimits, potent splittings, coproducts, and preserve the tensor products involved. So we have a TwoRig map that, on the one hand, just simply forgets the differentials wherever there. So we have this TwoRig map here, which I'll just call U for underlying. But we also have a TwoRig map, and this is kind of the crucial point, that takes homology. So there's a TwoRig map from Z mod 2 graded chain complexes to Z mod 2 graded objects just by taking the homology. And the crucial thing that we need to observe here is that if you set up the symmetric monodal structure correctly, then the homology, in the sense of this functor, will actually preserve tensor products. That's called the Kuhneth formula, which you may have studied in algebraic topology. Okay, so we have two TwoRig maps. And the Euler formula says that the quotient map that we use to get to the K-theory will actually co-equalize these two things. That is the Euler formula. So Q takes a pair C0, C1 to their virtual difference, and same over here. So we're saying that Q co-equalizes these two maps, which arise at the categorified TwoRig level by applying U and H. So although we can't categorify negatives directly, as in here, we at least have a proxy that we can operate as long as we operate this pair of maps here, a pair of TwoRig maps. And I can even say a little bit more. So the little bit more is that there's a little proposition that if we're dealing with the rig of isomorphism classes as cancellative, then it turns out that Q is actually not only co-equalizes, but is the co-equalizer of that pair. And there's an important takeaway from this. So there's a little heuristic where the idea is that if you are studying the K-theory of a TwoRig, and if you wish to establish an equation holds in that K-theory, then perhaps your best and most illuminating option is to raise it up to the level of TwoRigs. So start with a representative of one side of your equation at the TwoRig level, which will be, an object of this. It would be a Z mod 2 graded object, and see whether you can put a differential structure on that pair, in effect lifting up to the level of differential graded things, so that when you take homology, you get the other side of the equation. And what the proposition guarantees is that this is always possible. So if you have an equation that you suspect is true, if it is true, you'll certainly be able to apply this procedure of taking a Z mod 2 graded object, lifting up to a differential structure, applying homology, and out pops the other side of the equation. That's, in my opinion, an incredibly important heuristic, and I've not been able to really find it anywhere stated as such. So this is a heuristic that made a huge difference in our paper, and that's the basic punchline that I want to get across, is that this Euler characteristic idea comes to the fore and saves the day in terms of establishing important equations in the K-theory of various structures. So to reinforce that, I'm going to describe something called Joyce's rule of signs. And this is something that he discussed in a few papers. There's a wonderful paper written for a conference of combinatorialists. This paper is in French, but it translates to analytic functors and species of structures. Is that how it goes? I think it is. Analytic functors and species of structures is a translation from the French, in which he introduces to great effect this wonderful rule of signs, which I'll describe not at the species level, but at a linear species level. So I'm going to ask you to imagine that we have a finitary linear species. So what that means is a functor from the groupoid of finite sets and permutations to vector spaces. And by finitary, I mean that almost all but finitely many of the values of f are the zero vector space, and all those values are finite dimension. That's what I mean by finitary. So anyway, to any finitary linear species, you can cook up a so-called polynomial functor. So what this is a kind of tensor product. So you have this functor here, f, which assigns to each in-element set a representation of a symmetric group on in letters. So Sn will act on this, say on the right, and Sn will act on a tensor product, infold tensor product of an object of your TwoRig on the left. So Sn acts just by permuting the tensor factors here, and you tensor those two together. But this is meant to be a kind of categorification of a familiar Maclaurin series or Maclaurin polynomial. So think in those terms that we're categorifying that. This expression makes sense for any object in a TwoRig. And what I'm going to do is I'm going to try to assign a meaning to what it would, try to explain what it would mean to substitute in for the variable x a minus x. So what would that mean at a structural level or at the K-theory level? So this is an instance of what is called plethism. And certainly the answer would be known to people who should know about it, representation theorists. But we're getting a kind of categorical interpretation of what's actually going on. So let me take you through it. So what we do is we interpret, yes, we will, if x is an object of R, then we will think of that object as belonging to a graded object where the negative part is just 0, so the positive part is just x. So you can think of x as, more or less identify x with x comma 0 as a graded object. And I say this expression makes sense for any object in a TwoRig, so this expression would make sense for the TwoRig GR. And then what we want to do is we want to replace x by minus x. So how do we do that? Well, we're thinking that it's 0 comma x, here's the credit and here's the debit, and 0 minus x would be what this object represents in K-theory. So minus x ought to be represented by 0 comma x, and we'll feed this graded object into this functor and just watch what we get. And it's not hard. I was thinking as I was preparing these slides, a lesson that I learned very early giving talks before people is never try to do a calculation before an audience, because you'll lose people and people start staring off into space. And I feel like I might violate this a little bit, but I'll try to be somewhat gentle. There's a note 6 that goes along with this where it gets a lot more intense, but you can read that on your own time. But anyway, we're going to calculate what the meaning of this in the TwoRig of graded objects. How do you calculate this? And once we do, then we'll consider its virtual class in K-theory. Okay, so let's start. So just to get our feet wet a little bit, I'm going to imagine a simple exercise where I imagine how the two-element symmetric group will act on the left on a tensor product of 2 copies of 0 comma x. So this represents minus x. Now, the nitty gritty is getting your hands on how the symmetry isomorphism works for Z mod 2 graded objects. Okay, some of you may have seen this. So the way the symmetry isomorphism works on graded objects is that, yeah, you have this transposition and the symmetric group sigma. And the basic idea is that what's going to happen is that you just swap the tensor factors. That's what the symmetry ought to do, except that when you're dealing with things that is responsibly in algebraic topology with Z-mod 2 graded objects, there is inevitably this business about signs where you need to, when you swap two factors, you may have to take into account a particular sign where P and Q refer to degrees of homogeneous elements. So if you have two elements of odd degree and you permute them like this, you need to throw in a little sign here. Let me say that a little bit more explicitly. So you have these two tensor factors, and this little x is concentrated in odd grade or in graded 1. So the P in question here is concentrated in grade 1, so P will be 1, and the other tensor factor is concentrated in grade Q equals 1, so the transposition will introduce a sign change -1 to the PQ, which is -1. So you have to throw in a minus sign when you swap two odd elements. And this comes up in, I guess, supersymmetry, more generally in quantum mechanics, when you swap two fermions, you'll introduce a negative sign. So those are the two components here. Interchange the factors, throw in the -1 if they're both odd. And finally, I'll mention that the tensor product here lives in the grade got by adding up the degrees. So 1 + 1 is 0 mod 2. Okay, that's a little warm-up exercise to describe how a symmetric group will act on an odd object. Okay, generalizing a little bit, we have that Sn acts on an infold tensor product. Again, more or less the same way, by permuting the tensor factors as in the usual kind of way, but also taking into account that you may be introducing signs which depend on the sign of the permutation. So you'll have this little factor thrown in for an infold tensor product of odd objects. And moreover, this infold tensor product lives in grade n modulo 2. Those are the basic ingredients that we need. So because of the sign of the permutation, we're getting into the neighborhood of the sign representation of the symmetric group. And what we are finding is that when we substitute in -x into this polynomial species, what we get is the polynomial is a polynomial functor where its value at an n-element set will be gotten by taking the original value of f, but then tensoring by the sign representation and keeping track of the grade in which things live. It will live in even grade if n is even, and will live in odd grade if n is odd. When we pass to interpreting this in K-theory, what we find is that substituting in -x in for x leads to this explicit computation where, you're getting -1 to the n. So yeah, if n is odd, you're in the debit column. If n is even, you're in the credit column. So -1 to the n. And that's Joyel's rule of signs, which he uses in this beautiful paper that I mentioned before to do a very interesting calculation in which he calculates, this is getting a little far afield, but he calculates the structure of the Lie operad by doing various categorification tricks in which this makes a very special appearance. So that was just a little taste of what we do in our paper to account for negative operations and substituting them into other operations. And with that, I thought it would take me until 8:30 to get there, but we can stop here a little bit early. I want to thank you very much for coming by, and I wish I could see you beyond seeing you on the computer screen, but maybe in 2023, if we're lucky, I'll be able to come to New York and see some of you again. Anyway, thank you for your attention, and that will be all for now.
Thank you very much. Thank you. Thank you. Any questions? Okay.
I just wanted to say that Joe has been telling me about this paper and how happy he is with it. And I found it a bit scary. And I wanted to thank you for this talk, which sort of is a nice invitation to encourage me to get my feet more wet with it. So.
Oh, my pleasure. Yeah, I'd love to talk with you about this. It's a long paper, so it's over 50 pages long, and yeah, scary. I'm sure it is, because I mean, we go into a lot of nitty-gritty details, but once you see people give a talk on this stuff, it becomes a little less scary usually. So you got a little piece from Joe, and you got a little piece from me, and the three of us have been kind of doing the circuits and giving talks on this. In my opinion, quite lovely material. So I'm glad to see you here, Gersha. I actually don't see your face, but I'm glad to see that you are here. So.
I was wondering if somehow categorification can be not an art, but actually a functor in some sense. I mean, like from a topos to a cosmos or something like that. I mean, Ross Street usually comes. Why is it so hard to make it?
You said from a topos to a cosmos. Is that what you said?
Right.
Yeah. Funny you should use those words. I'm talking with Mike Stay, and I think what he would like to do is come up with examples of cosmoses, that's a bad word, cosmoi, so that when you apply linear logic to it and consider coalgebras for the exponential modality, bang, you get a topos. So that's a little side project, which you've just reminded me of, going from a cosmos to a topos, but you turn that around.
That's called decategorification.
It's called what?
Decategorification.
Oh, okay.
I was gonna.
It's possible that I overstated that it's merely an art. I didn't say merely an art form, but there are some aspects that can be mechanized. So a very early paper in categorification was written by John Baez in 1997. And that is in a workshop on something like higher categorical methods, hosted by Ezra Getzler and Kapranov, however you say his name. And the title of Baez's paper is Categorification, where he actually goes a little bit into the detail using things like opitotes about how one categorifies, say, a monoidal category into a monoidal bicategory or things of that nature. So, I mean, there's some aspects that can be mechanized. It's not completely an art form, but I mean, there is a certain amount of creativity in how you're going to lift in other situations, as I've been trying to indicate in this talk. Now, what you said, I'm not immediately connecting with. So,
well, if you think of a topos as a generalization of the category of sets, and you think of a cosmos as a generalization of the two category of categories, so then you're trying to go from a topos to a cosmos. That's what categorification is.
So I understand that when I hear the word cosmos, I'm thinking of a Benabu cosmos. And it sounds like you're thinking of a different notion.
I'm thinking of more, Ross Street has a few papers on that. All right. Anyway, so it's just a passing thing. I mean, everyone comes up against, how that categorification is not easy, or there's no formal way of doing it. I was just wondering why. Why is it so hard? Yeah.
I think in many cases there are actually choices, and they're equally viable choices. So I mean, one example might be the Shanuel paper I alluded to, where he talks about semilinear sets. But he's saying, there are actually a lot of categories which can play the role of E. They may have some structural similarities, but you could take semi-algebraic sets. That's a small example of the fact that I think there are potentially many different ways of categorifying, which would, be equally satisfactory as categorifications. Yeah. I don't know if that's satisfying to you, but
No,
there's
it's perfectly fine. Anyways, any other questions? Otherwise, I'd like to. First, I'd like to just say that Todd, it's always a pleasure, and you're always invited to give another talk whenever you're ready. This is the last talk of this semester, and next February 2nd, Ralph Wojtowicz is going to be talking, and we're starting a new thing. You're all welcome to come. I'm going to just shut the recording, and then we can continue talking.